All right, so now let's look at some applications of the Grothendieck spectral sequence. So remember, our Grothendieck spectral sequence looks like we start with some abelian categories and some left exact functors between them. So these are abelian cats, and we need them to have enough injectives, really just A and B, but let's just say that they have enough injectives. And then we have this other condition that F takes injective objects to G acyclic objects. Okay, and then we have this first quadrant spectral sequence that looked like the E2 page was the pth right-derived functor of G applied to the qth right-derived functor of F applied to A, and that cooked up for us the right-derived functors of the composition G after F applied to A. Okay, so for this video, I want to let R to S be a map of commutative rings. I could probably generalize away from commutative, but let's not bother. Just in some contexts and not others. I don't want to worry about it. Okay, so this makes S an R module. And I won't really refer to the map explicitly. I'm going to be kind of lazy in my notation. Now I want to take some S module and cook up some left exact functors from R mod to S mod to abelian groups. Okay, so these will be playing the roles of F and G in our Grothendieck spectral sequence, and so the whole point is that we'll get a spectral sequence. So what should these functors be? Well, I'm going to take F to be Hom, R linear Homs from S to something. Okay, so again, I'm implicitly using that S is an R module and not really referring to the map. Okay, and then for G, I'm going to take S linear Homs from this S module A. Oops. Trying to make this all readable to something. Okay, and remember we just saw these are both left exact. This should be left exact functors. And these are both left exact, so great. And what does their composition give us? Well, our spectral sequence is supposed to cook up something about the derived functors of the composition, so let's just check. We get Hom SA to Hom RS to something. And by adjunction, the adjunction between tensor and Hom, that's really Hom over R of A tensor S with S to something. Okay, and then of course that is just, well, the S's cancel here in a sense. Okay, so we have Homs, R linear Homs from A to something. Okay, all right, so that's what this spectral sequence should be cooking up. Well, we need to make sure that everything applies, so these are left exact. Maybe I'll check that off. That's all well and good, but we also need to check that if J is some injective, I guess I mean injective R module, because I want to look at F of it, then the question is F of J G acyclic? If so, we'll get this Grothendieck spectral sequence. Okay, well, asking whether this F of J is G acyclic is the same, maybe let me not get the F and G off the page. Okay, so that's the same as saying, do the higher derived functors vanish? So we want to look at x'd I s, right? That's our g. The derived functors of g will be x'd over s. And if we take a with Hom r s j, right? So I just took all of this stuff and fed it in. Then so this is my f of j, and then I'm feeding it into g, and then asking about the right derived functors. The question is, does this vanish for higher I? Well, I'm really going to write down basically the same thing. So Hom s blank Hom r s j, so ignoring the a for a moment, this is isomorphic by the same adjunction of tensor and Hom to Hom r blank tensor over s with j, and again, as above, the s's cancel in a sense, and so we have Hom over r blank j. Okay, but this functor is exact, right? We're homming to an injective, and so this other functor is exact, and so the higher x's vanish. So all our higher x terms vanish, and yes, f of j is g acyclic. Okay, so we have a Grothendieck spectral sequence. And what does it look like here? Well, I'm going to call this a theorem because it's often presented as such, but it's kind of turning out to just be a corollary at this point. You can prove this independently without all of this machinery if you want, but we get a base change theorem for x, and what does that look like? Well, it says there's a first quadrant spectral sequence, the Grothendieck spectral sequence for these functors, and so just plugging that in here, that's E2PQ, should be x over s, p, in dimension p, and then we take a, and here we have x over r. Maybe since things are off the page, it's helpful to look here, right? So this is supposed to be the right derived functors of g composed of the right derived functors of f applied to my thing. Okay, now I don't want to assume that it's injective, so let me just call that thing b. Okay, and then this should converge to the composition. And remember, the composition looks messy, of course, but we saw that by adjunction, it works out quite nicely. It's just going to give us that Hom over r, and so the derived functors are x over r with these things. Okay, so I think I said that kind of strangely, but if you go back and check all of the indices, then and which Hom is which, then you'll see this is exactly what we get. Okay, so similarly, we had this other Grothendieck spectral sequence for left-derived functors. I won't spell this one out in as much detail, but I could come up with a spectral sequence using some right exact functors. So let's say we went from R mod to S mod to abelian groups again. So I'm still using that map of rings R to S. I want to come up with an F and G here, and so here I'll tensor over R with S. Watch out, there's a typo in Weibel there. Though there is an entire list of errata for Weibel, so you might want to check that out if that's where you're looking. Okay, and then what's my G? Well, I'm just going to tensor over S with B. So B is some S module. Okay, and what is the composition? Well, okay, what does it do to some A? Now we should take A, tensor over R with S, and then we should tensor that over S with B, and so again the S's cancel, and we get A tensor over R with B. Okay, and I think I've done enough tedious verifications for you recently, so let me say that I'll leave it to you to check that we have that G acyclic condition. for f applied to some projective. Okay, I think it's probably going to come from projective implies flat. In any case, then we get this other base change theorem. So using these and their left-derived functors, we get a base change for, well, the left-derived functors here are Tor. So for Tor, and the Grothendieck spectral sequence says there's a first quadrant spectral sequence. That starts with E2 term coming from the left-derived functors applied to each other. So here that's Tor over S of Tor over R of A with S, and then take that with B. And that should cook up for you Tor of the composition. And we checked the composition really just comes down to tensoring over R. So this is Tor over R of A with B. This is coming from this calculation right here. Okay, maybe let me just, as long as we're here, say one very quick application that you may or may not have seen before. So I'll just use this second one, this base change for Tor. So this comes up a lot, I think, in algebraic geometry, but also in Spectra sometimes, though I haven't said quite how we want to relate all of this to Spectra. But of course, we end up computing Tor when we're looking at smash products of things. So, okay, that's the relation there. So remember, we had this map of rings from R to S. Suppose S is flat over R. So that just means that tensor over R with S is exact. Of course, it's always right exact. Here we're just saying that it's completely exact. Well, what happens if we wanted to look at this Tor, this base change for Tor spectral sequence? Then we'd have these Tor Q R terms for things like AS, but these are all 0. Right? If it's exact, there's no higher Tor terms, because this is just the left-derived functor of A tensor over R with S. So this is 0 for all Q greater than 0. And so the spectral sequence collapses right away. And in fact, I think this is what people often want in algebraic geometry, as I said at the beginning of the course, that you just have a spectral sequence that collapses. So what do I mean by that? Well, when I look at higher Q things, everything up there is 0, right? Because I don't have anything for Tor Q over R. Okay, so what do I have in degree 0? I have things like A tensor over R with B. I've got Tor 1 of A with B, and so on, higher Tor terms. Okay, but the point is this is all concentrated at height 0, so there's no room for differentials. So that's what I mean by the spectral sequence collapses. This E2 term is just our E infinity term. And what we learn then is that by plugging these things in, that if we look at Tor over S in degree P, A tensor over R with S with B, then we immediately just get the Tor for the composition. So all I'm saying is that the spectral sequence, there's not much there. There's only this 0 line. And what do we have on that 0 line? We're going to be taking Tor over S of this, and so we just get the thing at the end, these Tor with AB. Okay, so this is sometimes given as a theorem in homological algebra called flat base change. And this isn't the only way to prove it, again, but kind of a nice spectral sequence consequence. Okay, so I want to save most of the interesting applications for people's presentations who are going to be talking about these applications in algebraic geometry. But so in the next video, what I'll do is start talking about how do we actually construct this Grothendieck spectral sequence how do we see it as a spectral sequence coming from a double complex?